let H be a subgroup of a group G. The left cosets of H in G are the subsets of G of the form AH. A is inside G. So left here is that the arbitrary element of G is multiplying H on the left. And what is this? AH. So these are called the left cosets of H. Similarly, the right cosets of H are the subsets of the form and this again analogously this means H times A, where we run over all a little h in H. Okay, let us look at this a little bit more in detail. Okay, some small examples. Okay, suppose we take Z. And we know that if we have any subgroup, then it is generated by the small, one element, which is the smallest. If you have a non-zero subgroup, then it is generated by the smallest positive integer in that subgroup. Okay. So let n be inside Z, n greater than 0, okay, and let H be the subgroup n times Z. What are the cosets of so H consists of minus 3n, minus 2n, minus n, 0, n, 2n, 3n, and so on. This is what H is. Okay. Now, so the notation here we wrote the group as group operation as multiplication. So we just put them next to each other. In here the group operation is addition. So we will write, let us say 1 plus H. Okay. So this is the left coset. Okay. That's okay. This is things of the form minus 3n plus 1, minus 2n plus 1, minus n plus 1, 1, n plus 1, 2n plus 1, 3n plus 1, and so on. Okay. So in general, if m is an integer, then the left coset m plus z, sorry, m plus h. M plus h is analogously minus 3n plus m, minus 2n plus m, minus n plus m, m, n plus m, and so on. Okay. And observation, m plus h is equal to, in this example, m prime plus h. So these are equality as sets. or subsets of so this equality here as subsets of Z, if and only if so these are just integers that have value 1 modulo n. 1 plus h is 1 modulo n, integers whose value is 1 modulo n. M plus h is integers whose value is m modulo n. But m modulo n and modulo means if m is bigger than n, we can just subtract that, and in modulo n we would still have the same value. So using that argument, one can see that this is if and only if m times m prime is inside h. So so this is true in general. Let us just prove that. So we had earlier observed that if you take two cosets, left cosets of h in general, okay, ah and bh, then either they are equal or they're completely disjoint. So it's a similar argument as that here. Okay. For all a b inside G, ah is equal to bh if and only if. Actually, I forgot if I proved this statement earlier. A b inverse is inside H. Okay. Maybe I put this as an exercise. Sorry, I forgot to look up that day's notes to check if they had proved this. So I leave this as an exercise, if I have not done it already. So first, the exercise is first go back through your notes and determine if you have already proved it. If you have not proved it, please do this as an exercise. I will. Okay. Yeah. So that is just the idea of cosets, and just to recall this idea of cosets. Okay. So one thing that I okay, so here is a proposition. The left cosets of H form left cosets of H in G form partition. Okay. So what does this mean? Okay. In case you have not seen this word partition of a set, this is what it means. Okay. So let X be a set. So as we progress, we will see that all the almost all the objects that we would come across ordinarily will be sets, and we put extra structures on. The notion of a partition is, at least the way it is used here, it is it is associated with a set. So of course, therefore, it will also apply to groups. Let X be a set. A partition of X is a collection, some xi in some index set I. It need not be finite, of subsets of X such that xi intersect xj is empty if xi is not equal to xj. So there, okay, and the union. So they are they are a collection of disjoint sets, subsets of X, whose union is X. So two different subsets in this collection will be completely disjoint. They will have trivial intersection, and they will cover the whole set X. In other words, so let's go back to this example. So if you look at any integer, it will be in one of these cosets. It will be in the coset H, which is 0 plus H. Okay. If it equals 1 modulo n, it will be in the coset 1 plus H. If it equals 2 modulo n, it will be in the coset 2 plus H, and so on. And it has to equal something modulo n, so it will be in that coset. And they are disjoint because given any number, it can only belong to one. It has a unique value. What it is mod. It has a unique integer between 0 and m minus 1, which has the same value modulo n. 0 and n minus 1, same value modulo n. So therefore, each integer will belong to exactly one of these partitions, one of these parts. So this is what we mean by a partition of a set. Okay. So let's just write down what this. There isn't much more to write down other than what we have just. Hello. Did someone have a question? Okay. So there isn't much to write down other than just to check the definition. Okay. So we have already checked that if AH is not equal to BH, then they are disjoint. That is because if there is an intersection, then A will belong to the coset determined by B, and B will belong to the coset determined by A, and then one can show containment in each direction, and therefore equality. Okay. So therefore, it suffices to show that the union of these things is inside H. Okay. Now note that for all A in G, A is inside AH, since E is inside H. A equals A times E. Okay. So therefore, G is the union of AH. And this gives a partition of the so this is exactly what we needed to do. Yeah. Another thing another observation is that all cosets have the same cardinality. Let G be a group and H a subgroup. Then for all A inside G, the function H going to AH, some little h gets multiplied to AH, A times H, is bijective. Okay. So the cardinality of the coset AH, or the order of that cardinality of the coset OH, is the order of the group H, subgroup H. Okay. So this is true for every A. So in fact, the cosets partition G into parts, each of which have the same cardinality as the cardinality of the subgroup. And as an immediate corollary, that if G is a finite group, okay, and H is a subgroup, then then order of H divides order of G. And the reason is that G is some A1H union up to proof to some AMH. Okay. So for some A1 through AM inside G, all of these have the same cardinality. I mean, if they're distinct, so therefore order of G is the sum of these cardinalities of these things.
So could you scroll up a bit?
Sorry, I have no idea why I, just a minute. I don't know why I skipped that much of, I mean, I thought page ended, so I did not. So let's go back. Yeah. Okay. So we can assume that these are all distinct because, I mean, if A1H is equal to A2H, then there is no need to take both of them. You can just take A1H. Right? So then, so we can assume that AIH is intersect AJH if I is different from J. This is empty. Sorry. Okay. And this is yeah. Okay. And so this is just M times the order of H. Another corollary of this thing is that if G is a finite group, then let G be a finite group. A is inside G, then the order of G, order of A divides order of G. Proof, apply above corollary to the subgroup generated by A. Let H be the subgroup generated by A. Then order of H is the order of A. Apply above corollary. So that is just a quick look. And this last result is, or maybe the previous result is called Lagrange's theorem. Okay. So a definition, one term that is used in this context. Okay. Let G be a group and H a subgroup. Okay. By the index of H in G, we mean which is denoted by this. Okay, we mean the number of distinct, the cardinality of a set of distinct cosets. It need not be, I mean, we will only work with finite groups. Set of left cosets of H and G. Okay. So we will work mostly with finite groups. I mean, at least when we want to think about this. Yeah, so which means this is just a number. Okay. But just because I didn't say G is finite or the number of cosets is finite, let me just use the word cardinality of the set of cosets. Okay. Yeah. So one more. Proposition. Okay. So let phi.
Sir, the index is the number of distinct the number of distinct
So it is, I mean,
the left cosets actually.
Correct. But when I say the set of left cosets, it's understood that the elements of a set are distinct.
Oh, okay.
Yeah. So that's why I wrote it as, I mean, if I wrote it as number of cosets, I should probably say number of distinct cosets. But because I wrote it as cardinality of a set of cosets, I presume that it is understood that it is distinct cosets. Okay. I mean, in a set, you cannot have elements that repeat. That
yes, sir.
So let phi from G to G prime be a homomorphism of finite groups. So then, what can we say about the order of the kernel and the image and things like that? Okay. Then the key observation is that order of G is the product of the order of two. As a corollary, order of the kernel divides order of G, and 3 divides order of G and order of G. So one is the thing that we need to check. Okay. Not very difficult, but we need to check. 2 will follow from 1, and 3 will follow from one and earlier discussions. Okay. 3 will follow from 1 because one says that in particular that image of phi divides order of G, and image of phi is a subgroup of G prime, so that will divide order of G prime also. So what exactly, what exactly is behind the proof of 1? Okay, so let's prove that. So now we have a group here. So I'll draw it with the picture. I will write these things precisely, but to get an idea of what it is. So this is G. This is G prime. Here is E prime. Here is. Now there is the kernel of this map. Kernel of this is phi. So this thing that I've written in red, this is the kernel. This goes to E prime altogether. Now, let us look at another coset. Okay. So this is some copy of a coset of kernel of phi. Maybe I'll draw that in different color. So this thing in green is a coset of kernel of phi. So this, okay, so let us see what happens to the elements inside this coset. So let us say this is a coset given by an element A times kernel of phi. Okay, so this is, okay. So what is, so let B be inside the coset kernel of phi. This is left coset. Left coset given by A. So let A is inside. Then phi of, so then we can write B as some A times G for some G inside kernel of phi. Okay. So now we can apply phi times, what does phi of B look like? Phi of B is phi of AG. This is phi of A, phi of G. That's the definition of, from definition of a group homomorphism. Phi of G is E prime. And E prime is the identity element in G prime. So this is phi of A. In other words, every element in the coset A times kernel of phi is mapped to phi of A itself. So that is every element in A kernel of phi is mapped to phi of A by phi. One observation. Conversely, suppose something is mapped to phi of A. Conversely, let C be such that phi of C is equal to phi of A. Okay. This would imply that C A inverse is inside kernel of phi, because C A inverse will get mapped to E prime, which is okay. This would imply that C is inside. Okay, maybe sorry, I should not have written like this. Just give me a minute. A times. Wait, I should just write C equals. Just for right, because A inverse, if you multiply both sides by phi of A inverse, you would get, and then I'll give us that A inverse C is here. and therefore C is inside A times kernel of phi.
Sir, sir, in the exercise that you wrote in the second page, I think.
Could you speak up? I can't hear properly.
Sir, in the exercise that you wrote in the second page, I think you have written the same way. A B
This way
inverse.
or the other way?
The other way. A B inverse belongs to H.
Okay, I will check.
Yeah.
I'll check after the class. If there is a mistake, I will update it. This is the correct way it should be written. Because you want to multiply A on the left side and conclude that C is inside A times kernel of phi. I mean, because we want to prove that C is in the left coset. If you wanted to prove that C is in the right coset, the other one would have worked. And which we will see. The left coset is also a right coset, but that is a separate. Okay, but that we will see. Okay, so if there is a mistake in my exercises, I will. I mean, when we write it, we should be careful. I agree that in this case it would not have made a difference, but that, but that's okay. So so in other words, what we just concluded is that if you take an element in the image of phi and look at its pre-image, okay, so in other words, okay, for all G prime in the image of phi, phi inverse of G prime. So you can think of this G prime as phi of A, as phi of A. For example, okay, this is exactly a coset. Is left coset. We will see that it is also right coset, left coset of kernel of. Okay. Conversely, every left coset of phi of phi kernel of phi is of the form phi inverse of G prime for some G prime in the image of phi. Okay. So we are still in the proof of this, but this is what is happening in the proof. Okay. So in other words, the number of cosets of kernel of phi is equal to the cardinality of the image. So, I mean, whatever we described is some general thing. We never used that G is finite or anything for this purpose. Okay. Now we're going to use that G is finite. Okay, maybe I should add a remark here. We have not used. Okay, maybe let me just make sure. This picture is only sort of schematic. I mean, there's nothing implied in. Okay. We have not used the hypothesis that G is finite. Okay. Whatever we have said so far is some generality. Okay. That if you have a group homomorphism, the cosets of kernel of phi are in bijective correspondence with the image. Okay. Each coset determines one element in the image. Conversely, each element in the image determines one coset. Okay. That's what we have done so far.
Sir, could you just roll up a bit? Okay, sir.
Okay. So now so now let's get back to the problem. Now suppose that G is finite. Then kernel of phi is finite. order of the image of phi is finite, and kernel of phi has exact the number of cosets of kernel of phi equals order of the number of cosets of kernel of phi equals order of image of phi. Okay, each of those things have the same cardinality, so therefore this is what was asserted in 1. 2. Two is that kernel of phi divides order of the kernel of phi divides order of the group. That follows immediately from 1. Okay. 3 follows from, I mean, 1/2 follows from 1. That order of the kernel of phi divides the order of the image of phi divides order of the group, order of G. Okay. Since G prime is a finite group, image of phi, order of the image of phi divides order of G. That is, so even if it didn't, I mean, all of everything that we discussed, I mean, part 1 and part 2 would go through without assuming G prime is finite. The only place where the finiteness of the order of G prime is used is for this last line.
Sir, could you repeat the last part of the first point?
I said everything that everything that we said in this proof.
Sir, the first point, I mean, the number 1. Order of G is order of kernel of phi into order of image of phi.
This statement?
Yes, sir.
No, sorry. What do you want me to repeat?
Oh, okay, sir. Sir, the last line I could not follow. That's why I wanted. Okay, sir. It's fine.
I mean, no, I can repeat. I just didn't understand your question.
Sir, I mean, this last, I mean, from where you derive that order of G is equal to order of kernel of phi into
this
order
one.
of image of phi. Yes, sir.
I mean, kernel phi is a subgroup, and each coset has the same cardinality as kernel of phi. And how many cosets are there? Equal to the cardinality of image phi.
Okay, sir. Yes, sir. Now I get it.
That is what this earlier observation is.
Yes, sir. Yes, sir. I can follow it.
So yeah, maybe okay, maybe it's a good idea to okay. Let me make some general remarks here. Main remark. So we talk about partitions, but where do partitions come from? Or in other words, so let f from x to y be a function. Okay. Then this collection f inverse of y is the image of f. Give a partition of x. Maybe you have not seen this yet, but this is some, I mean, this is a very common way of thinking about partitions. Or actually, that's a good question. You have seen equivalence relations before? I mean, has equivalence relations been discussed in Algebra 1, Analysis 1, or Analysis 2 so far? I don't know if I'm not asking if you've seen it before in school. I'm asking in CMI, has equivalence relations been discussed?
In discrete maths, equivalence relations has been discussed.
But that doesn't include the physics students, right? But not in Algebra 1 or in Analysis 1.
No, sir.
Okay, then I should actually spend one day doing that. Actually, the problem is that if maybe it is better if I do that. What time is it? I see. Maybe that is one issue. Yeah. Okay, then just give. Okay, so let me see if I should do that now or do more of.
Sir, could you just repeat how you got the third point once?
This one.
Yes, I mean the relation between order of G prime and
But
image of.
that, I mean, that is what we observed earlier, that if you have any finite group, any subgroup, order of any subgroup will divide that.
Oh, yes, sir. Yes, sir.
I mean, so the,
yes, sir. Yes, sir.
I mean, the underlying principle is this. The G, I mean, group is partitioned into cosets, and each coset has the same cardinality. This works irrespective of finite group or infinite group, it doesn't matter. This state, whatever I just said is true. I mean, the group is partitioned into cosets, and each coset has the same cardinality as that of the subgroup. Now, if these are finite, then you can actually count and then make this thing that order of a subgroup divides the order of the group. Okay, so before okay, let me at least finish a couple more things that I planned for today. But then for doing anything else, I would need to do equivalence relations. Okay. I mean, I could probably not do it, but that it will not help you. In any case, it will help you to see equivalence relations. Okay, we'll come back to this way of thinking about partitions when we do equivalence relations. That's probably why. Yeah. So we will revisit this partition business when we do equivalence relations. Okay, I just need to rearrange a couple of topics. And then so sorry, just give me 1 minute. I just need to think through this proof to make sure that I don't implicitly use ideas about equivalence relations when I write the proof. Just give me 1 minute. Okay, proposition. Okay. Let G be a group. Okay. And H containing K be subgroups of G. So K is the smallest, the middle is H, and then is G. Then we ask the following: what is the index of G inside K inside G? Number of cosets of K inside G. This is equal to the index of H in G times index of K in H. Okay. So we will prove, I mean, so the statement is true without assuming that these are finite. But then, of course, we need to know what we mean by countable infinity times an uncountable infinity sort of things. Okay, so I do not want to dwell on those topics. So we will just prove the statement only for finite groups. Okay, so if you don't assume that these indices are finite, I mean, the number of indices means number of courses is finite, then you have to worry about some infinite multiplication. So that requires more careful development. So let us just worry about this finite groups, or at least only when the indices are finite. So in other words, we are not assuming that G or H or K is finite, but only that there are only finitely many cosets of K inside H. In H and of H in G. Okay, but I mean, just to make it clear, I mean, distinction between, we're not saying that the groups themselves are finite. We just say that the number of cosets are finite. Okay? So, for example, if you look at Z, okay, you take any non-trivial subgroup of Z, it has only finitely many cosets, but neither Z nor the subgroup is finite, as we saw in the example earlier. If you look at the subgroup generated by 3Z, okay, then the cosets are the coset of 0, then the coset of 1, and the coset of 2. Every other element belongs to one of these cosets. So it has only 3 cosets, but neither the subgroup nor the group is finite. So we are only interested in the, I mean, we will prove this with this assumption. Okay. So let M denote the index of K inside H. In other words, K has M cosets inside H and N the. So what does this mean? In other words, there exists H1 through HM inside H such that H1K, H2K up to HMK are all the cosets. I mean, all the distinct cosets. Not only have we taken all the cosets, we've only taken them once. Cosets of H of K inside H. Okay. Similarly, there exist G1 through Gn inside G such that G1H to GMH are exactly the cosets, exactly the not are all the distinct cosets of H in G. Okay, so now so H itself is a disjoint union H1K union HMK, and G is a disjoint union G1H GNH. Now, G1H can be broken up into G1H1K, G1H2K, G1H3K, all the way up to GNHMK. So this is G1 G1H1K union HMK. That's the first thing, just G1. These are disjoint because if there is an intersection, it would have shown up in. So we'll check that. Let's do it slowly. G1, sorry, now for G2. Sorry, wrong font. G2H1K, G2HMK, and so on. GNH1K, GNHMK. Okay. So these are all cosets of K. So therefore we have written G as a union of cosets of K. Okay, so we would like, we want to know if these are all distinct. We need to check that these are distinct. So we want to show that what do we need to show? We need to show that this index, that is the number of cosets of K inside G, equals M times N. Okay. For which it is necessary to check that these are all. So we have already written G as a union of cosets of K. What we need to show is that there are exactly M times N in these things. Okay. Therefore, we need to show that if we take some Gi Hjk and some Gi prime Hj prime k, they are distinct unless I equals I prime and j equals j prime. We need to show that Gi Hj k is equal to Gi prime Hj prime k. Okay, so this is true for all 1 less than I less than n, 1 less than j, I mean I and I prime less than n, j prime less than or equal to m. Only if ij, the tuple, equals I prime j. Okay. So in other words, if either I and I prime are distinct or j and j prime are distinct, the cosets are also distinct. That's what we need to show. So one part is easy. If the index for G differ, then they belong to two different parts in the H cosets of G itself. Okay. If I is different from I prime, then Gi Hj k is a subset of Gih. Gih came from this ith piece here. Okay. So the first, so this is a maybe So this is the decomposition of and so on. So if I okay, and gi prime hj prime, it doesn't matter what j prime is, and gi h intersect gi prime h is empty. So that takes care of if I is different from I prime. So now assume that I is equal to I prime and j is different from j prime. But j is different from j. So in other words, we are looking at gi hj k and gi gi hj. Oh, I'm sorry. I should not have. Sorry. This I have not. Oops. It's a little. Sorry, I incorrectly stated that we have shown that it is a partition. We have not yet shown that it is a partition. We have just only shown that this is a. These are subsets of G1. G1K, G1H. Okay. We have not shown that this is, I mean, that's what we're showing now. Okay. Similarly here, this is just subsets. Okay. So because of that, if the i's differ, then they are actually subsets of two disjoint larger subsets. So they are themselves disjoint. Now we are looking at the same GI, but different HJ. Okay. So it's in here it is just one row. So then, sorry, then GI HJK equals. So we want to prove that these are distinct. Okay. HJK is GI HJ prime K. Okay. So now we can multiply by GI inverse on left side, or maybe okay. So this is what we have. Okay. So yeah, so multiply by GI inverse on the left side. To conclude that HJK is equal to HJ prime K, which implies that J equals J prime. Because we chose the HJs to be distinct. So therefore, so we have proved this. Okay, so that there are, I mean, in this decomposition, it is actually all of them are distinct, and therefore, K is M. This is what. Okay, so maybe I'll do one more thing about subgroups, normal subgroups, and then next lecture I will start by doing something about equivalence relations and partitions. Okay. So we talked about right cosets, although we proved everything about left cosets. Similar results will also hold for right cosets. So I am not going to repeatedly state them, but we would like to understand the following. Okay. Proposition. Let H be a subgroup of a group G. Then the following are equivalent. 1. H is a normal subgroup. In other words, it is closed under conjugation. G, H, G inverse is inside H for all G inside G. And for all H inside H. For all G inside G, so this is okay. So this is just a abbreviation for the set GH G inverse H inside H. Just like writing for cosets. Okay. So this is a subgroup of G. Okay, that we can verify later. Okay, 3. For all G inside G, GH, which is the left coset, equals HG. That's the right coset. Okay. And 4, which looks like a much weaker condition, every left coset of H in G is a right coset of H. So this condition is potentially very much weaker than saying anything else. Here we are saying that the left coset of H given by little g is also the right coset of H given by little g. Some of these statements are easier to prove than others. Okay. So 1 implies 2. So 1 says that for all H in G, so let G in G, then GH G inverse is a subset of H by 1. Right? That's because this is just an abbreviation for the collection GH G inverse little h is inside capital H. By 1, the individual elements are in the set capital H, therefore the union is also in there. So by now apply so but okay, let's write down what this means. Okay, so let H be inside H. I mean conversely. Okay, let's be inside H. Then GH G inverse is equal to some H1 for some H1 inside H. Right, because it's inside H, which implies that H which is equal to G inverse H1 sorry, just a minute. Yeah. Okay. Maybe I should. Sorry. Sorry. Let me make sure that sorry. Let me make sure I put the quantifier. Yeah. Sorry, let me rewrite the converse. Conversely, apply 1 to G inverse. Okay. So that would say that G inverse HG is also inside H. Okay. So one says that for every G in G, this statement is true. Okay. So you can apply 1 to both G and G inverse. I mean, fix any G, you can apply 1 to G and its inverse and any other element you want. Sorry, I should have started like this, because if I try to fix this at the end, it will apply 1 to G inverse to get this condition. But what does this mean? Okay, so let H be inside H. This implies that G inverse HG is inside H, which implies that H, which is G inverse HG, G inverse, this is inside GH G inverse. So in other words, H is inside GHG. So first we showed that GHG inverse is inside H, just directly applying 1. Then applying 1 to G inverse, then just small observations, we show that H is inside this one. So therefore, H is equal to GH G inverse. This is 2. Okay, so key thing, key thing is to get this. When we work backwards, we will need to show that for every little h, which is inside GH G inverse. So we need to take G inverse to the side, and then we realize that we should have begun by applying 1 to G inverse. If you apply 1 to G, we would just get this. 2 implies 1. This is more direct because 2 says this and 1 says something substantially weaker than that. But it is not, because it is universally quantified over all G. By let G be inside G and H be inside H. Okay. Then GH G inverse is an element of GH G inverse, which is equal to H. So this is what we want to do. This is by 2. Okay. So now, what are the remaining statements? So now we want to relate this condition to left and right cosines. Okay. So 2, and we'll now relate 2 and 3. So we want to show that GH is equal to HG. So we will like to prove both equalities. So first we show that. So let H1 be inside H. Then GH1 G inverse is inside H. So GH1 is inside HG. Maybe just once, let me clarify this. Equal to H2 for some H2. Sorry. This implies that GH1 is H2G. This is inside HG. Okay. That's what we want. GH1 is inside HG. Therefore, and this H1 was arbitrary, so this proves this. Similarly, we need to take some arbitrary element inside HG, so call it H3 times G. So I'll just leave that as an exercise. other direction exercise. We just have to use the fact that G inverse is equal to H. Okay. Yeah. So 3. So now assuming this, we need to show that G inverse is equal to H. Three implies 2. So let H be inside G. H be inside H. Then G inverse. So what we know is that GH is equal to some H1 G for some H1 inside H by 3. This implies that G inverse is inside H. So therefore, okay. So this is what we have. Now, let us take this equation itself and manipulate. Okay. So we multiply G inverse on the left and then G inverse on the right. Okay. So we are cancelling G on both sides. So we will get H, we get H G inverse. So I'm multiplying now both sides, G inverse on both sides on the right. So it cancels this one. Now I'll multiply both sides on the left to get, sorry, just give me a minute. This is not, sorry, my mistake again. Just use it for the, so remember 3 is again universally quantified over all G. Right. So now apply that for G inverse. Apply 3 to G inverse to get a similar conclusion, which is G inverse HG is inside H. So this implies that H is inside G inverse. And this is what we needed. So you'll have to do a similar trick here also. So 3 implies, so actually the 4 implies 3 is the one that takes some thought. And maybe I'll do it next. So I'm already over time. So I'll stop here and I will finish the proof of this, then discuss equivalence relations and come back. Okay, because that's, I mean, to develop the next topic, which is quotient groups, it would help if you're familiar with the notion of equivalence relations. Okay, so we'll do that first. The next, I mean, we will finish the proof of, complete the proof of one more thing in this step of this proposition. Then we will discuss equivalence relations, and then we will go on to doing quotient groups in the next lecture. Okay, I'll stop.
Thank you, sir.